Okay, so we are very happy to have Professor Richard Szabo from Heriot-Watt in Edinburgh. He'll talk about a homotopy double copy of non-commutative gauge theories. So please start.
Right. Okay. Thank you, Masashi. So thank you very much for the invitation. Masashi and I have been trying to find a date for what seems like many months now, but because I've been very busy. But thanks for having me. So I'm going to talk about some work that's about a year and a half old now. So I guess by today's standards, it's not so new, but so it's I'm going to explain what the talk is about. You see the title there. This talk is a bit technical, so it's got technical details with some clear physical messages, which I'll try to emphasize throughout the talk. So the talk is based on a paper I published with my student Guillaume Trajani, who's now finished. About a year and a half ago. And then there's a short conference proceedings, which summarizes the results of that paper and also what I'm going to say today in more and less technical terms. So if you're interested and you want to see a kind of quick summary of the kind of physics behind what I'm talking about today, you can visit this paper here. But I'm just going to get right into it, start explaining the background and what is the type of problem that I'm interested in here. Um, so this talk is about the double copy, which I'm sure most of you have heard about. And I'll try to explain a little bit about what that is. But the origin of the double copy actually goes back to the mid 1980s, the famous KLT relations between open and closed string amplitudes. Um, and just very schematically, the relation is between tree level closed string amplitude, so a sphere amplitude, and the copy of two copies of open string tree level amplitudes, which are of course disk amplitudes. So the kind of the topological reasoning behind the duality is if you take a sphere, you can cut it along its equator, and that splits it up into two disks. So if you glue the two disks together along their common boundary, you get a sphere. And this could be made very precise at the level of tree level amplitudes in string theory. So if we take the zero slope limit, the field theory limit of the string amplitudes, of course, the closed string amplitudes become tree level amplitudes in gravity, and the open string ones become gauge theory amplitudes. So this is sort of the idea behind the double copy is that the gravitational amplitudes are somehow given by gluing together two copies of gauge theory amplitudes. So a little more analytically here. So if we call um, the tree level gauge theory amplitudes with these AN, there are two copies. There's a left one and a right one. Then the gluing operation that I mentioned up here is obtained by summing over all words, and just to think of these words are they're permutations of the labelings of the external particles in a tree level graph. There's some kernel that glues the two left and right copies together. And when you do that sum, you on the left-hand side, you get just the tree level amplitude for gravity. Okay, so here these ANs are not the full amplitudes you calculate in a gauge theory, but they're the color stripped amplitude. So the full amplitude would be obtained by taking these ANs. Here are the usual color factors from your non-abelian gauge algebra, and then you sum over all permutations up to cyclic ordering. So you got tree level, you can factorize your gauge theory amplitudes in this way. And of course, it's the color stripped amplitudes that appear in this formula, because on the left-hand side, which is gravity, you should have no color factors. Okay. Um, so this is so this was the formula written down by KLT many years ago. It was realized much later after KLT, that these momentum kernels here can be determined in terms of a special type of scalar theory called the biadjoint scalar theories. So this momentum kernel, Sn, is actually the inverse of what they're called these bicolored scalar amplitudes. And I'll explain what that scalar theory is later on in the talk. Okay? But this is the key idea to start with, is what the sort of origin of the double copy comes from string theory in this language. So that's the first idea, is about double copy. Now, this talk is about how the double copy paradigm fits into non-commutative field theory. So let me just quickly review what these theories are. So if we look at open strings in a constant background B field, so a Neville-Schwartz B field, then what's very well known by now is that they see a different type of background geometry than the closed strings do. So if the closed string background is given by some constant metric, and of course this Cal-Bremond field B, then open strings see a different metric that I'll call capital G, and also a bivector that replaces this two-form B. There's an explicit formula you can write relating them. This is not, this can be made very explicit, but I don't need the explicit formula, so I'm not going to write them down here. Okay. And so now the observation is that if you look at the tree level color stripped open string amplitudes in the presence of the B field, they're going to depend on these two parameters, G and theta. Then they have a very simple dependence on theta. So they all factor, there's a phase factor that comes out from the usual amplitude without the B field. So if you take the amplitudes I had on the previous slide, which were for B equals 0, and so this bivector theta is 0, and then you just dress them with some phase factors. So this cross product of momenta that's written here is defined by this formula, where this theta mu nu are the components of this constant bivector here. So that's the observation, and so now where non-commutative field theory comes in. If we look at a special field theory limit of this situation, so this is what's called the Seiberg-Witten limit, where we take the zero slope limit, but we also simultaneously scale the closed string metric down to 0. So you completely decouple the bulk string dynamics from the boundary dynamics where the open strings live. Then this gives a field theory, but it gives a special field theory where the interactions, which would be given by pointwise products of fields, are replaced now with what's called the Moyal-Bale star product of fields. So if we have two U of n valued scalar fields, the star product is defined by this type of formula here. Okay, and so if you're not used to these type of things, the way you understand this formula, so there's a bidifferential operator inside here. It acts on the legs of the tensor product here, and you should expand the exponential as a formal power series, let the differential operators act on the corresponding legs, and then the dot here means just to take the pointwise product of the resulting expression. Okay. So here, theta is very roughly related to the inverse of the B field. But this is, where all the excitement from non-commutative field theory came in the late 90s, because then the low energy dynamics, if these open strings are ending on D branes, then the low energy effective field theory on these D branes is a non-commutative gauge theory. Okay. So these were the observations in the late 90s, nothing to do yet with KLT. And it sparked a flurry of activity in trying to understand various things about these non-commutative theories, okay, which I'm not going to go through. Okay, so those are the two different pictures now. So we have now this scenario where we have the open strings with the B field, and we can ask what happens to the double copy prescription. So how do the KLT relations that I wrote down on my first slide change? And it turns out this is completely trivial. It's a completely trivial relation because we know, given this factorization that we have here, we know what the KLT relations are for the ordinary amplitudes without the B field on the right here. So we just have to invert all of these amplitudes in terms of these phases and then write down what these KLT relations are in the presence of the B field. Okay, so that's what the formula is written here. Here are these open string amplitudes in the presence of the B field. And what happens now, the momentum kernel gets modified in a very trivial way, just by the corresponding phase factors that I wrote down on the previous slide, right? So now there's a slight difference, of course, that these amplitudes now depend on this open string metric rather than on the closed string metric. But what happens, you see, is that nothing changes in the KLT relation. On the left-hand side, I haven't changed these gravitational amplitudes. They're just the usual amplitudes of general relativity, but expanded perturbatively about this background open string metric, capital G. So the answer, what are the KLT double copy relations with constant B fields, is very boring, okay? And what it says in the field theory limit is that the double copy of noncommutative gauge theory, which I write here symbolically by saying it's the square, just gives gravity, okay? And by gravity, I don't mean any esoteric noncommutative version of gravity, but just ordinary gravity. And you see, this was my original idea or interest, was to go look at the non-commutative gauge theories in this double copy framework, was to see if there's a nice way to think about non-commutative gravity that's been studied a lot in the language of these double copy relations. But you don't. So it's a very boring result. And if you were pessimistic, you could stop the talk right here and say that's the answer. But actually, if we probe into this very boring result a bit more, it does raise some interesting theoretical questions. And I'm going to talk about two of those questions today and hopefully convince you that these questions lead to answers that give interesting perspectives on the double copy. And actually, it introduces a lot of new theories, which we didn't know about before. And at least I didn't know about these types of theories before. And that's what I hope to address in this talk. Okay. So there are various questions that come out of this, and I'm going to focus on two of those questions in this talk. And the first question is simply, so we've modified these KLT momentum kernels up here by these phase factors, but remember the usual KLT momentum kernel I said came from a special type of biadjoint scalar theory. And so the question is, how do these kind of dressed KLT amplitudes arise from a scalar theory? So what is the scalar theory that underlines this relation for the B field modified momentum kernel? What is that theory? Okay, so that's one of the theories we'll answer. And actually, the answer to this question is going to come more towards the end of the talk. We'll have to build up many things before that. So there's a second question that comes up, and to state that question, let's look at another perspective on the double copy. And this was introduced much later than KLT, so back around 2008 by BCJ. And it's this notion of color kinematics duality. So if we take a gauge theory amplitude, which I'll write here as ANLR, so they're either two copies of the same gauge theory amplitude, or you take two different gauge theories and you treat them as left and right sectors, and then you try to copy them together into some effective gravitational theory. But the statement by BCJ it's an assumption. It's supposed that you can write the amplitudes in this schematic form here. Okay, so what this formula means is this is just tree level amplitude. So the sum over I is over all tree level graphs in your theory. The C's here are color factors. Okay, so they depend on, let's say, combinations of the structure constants of your gauge algebra. The D's are just products of propagators. So you write down a tree level amplitude, you're going to have propagator factors coming in, and that's what these D's are. So they're products of Mandelstam invariants. And then the N's are kinematic numerators. They're all the other things that come from the interaction vertices. But the point here is that you can strip, as I mentioned before, you can strip the color from the kinematics, from the kind of kinematical factors in this way. And so this is the assumption. Now this is not unique. This is a kind of choice of basis to rewrite the amplitudes ends. It's not unique, but we assume we can do that in such a way that there's what's called the color kinematics duality. So color kinematics duality states that any relation among these color factors will have a mirror relation in terms of these kinematic factors. Okay, so for instance, if you write down a 4-point function, you know that there's going to be products of structure constants, and they have to sum up and enforce the Jacobi identity for your Lie algebra. So one such relation among color factors would be the Jacobi identity that's satisfied by the structure constants. And then the claim is that the corresponding kinematic numerator factors also satisfy a similar type of Jacobi identity. So these are what are called generalized Jacobi identities. And this is very interesting because what this states is that what's hidden inside these tree-level gauge theory amplitudes is some algebraic structure that we didn't know about. You know, we've been studying non-abelian gauge theories for many, many years now, but there's some kind of hidden algebraic structure that's controlling the kinematic structures of the amplitudes. And so this is something that people refer to as the kinematic Lie algebra of a theory, and really one of the big points of investigation nowadays in the double copy literature is to understand what this kinematic Lie algebra is. Okay. But anyway, what if you can do this factorization and color kinematics duality holds in this sense, then there's a very simple prescription to get the double copied gravitational theory. You simply replace the left, say a left, you replace a color factor. So let's say for the left amplitude, you would replace the color factor by a right one. And conversely, the right one, you replace the color factor by a left one. And so you get an amplitude that looks like this. So the color is gone now. It's just given by products of these kinematic factors. And that's another way to construct these double copied gravitational amplitudes like I had before. Okay. So that's the perspective on the double copy based on color kinematics duality. And I just mentioned here that where this biadjoint scalar theory comes from that I mentioned before would be to do the converse operation, where if I take these kinematic numerator factors here and replace them by some color factors of a possibly different Lie algebra, this would give me the amplitudes of what is called the biadjoint scalar theory. And that's often referred to as the zeroth copy in this story, because if you imagine taking a gauge theory and double copying it with this biadjoint scalar theory, if you think a little bit about what happens here, then the amplitudes you get are just going to return those of the original gauge theory. So this biadjoint scalar theory acts as kind of the identity operation in the space of double copied theories. Okay. And that's because in this biadjoint theory, the color factors do act like the kinematic factors. Anyway, that's this is this kind of well-known story about color kinematics duality. And now the second question, the second and final question I'm going to address in the talk is okay, what is the meaning of this color kinematics duality in non-commutative gauge theories? Okay, so what does this mean when we look at amplitudes in, say, non-commutative Yang-Mills theory? Okay. And so why is that a question? You might wonder, well, why is there anything to ask there? And the point is that what we assumed up here is that we could factorize. We could factorize the color factors from these kinematic factors. So there's this color stripping that we did. And this is the problem. So let me try to explain that a bit here. So rather than a duality, there's a mixing of color and kinematics in non-commutative theories. And again, if you're an expert on the topic of non-commutative field theories, this is well known. This is nothing new here. So let's see what that is. So let's look at this space, this algebra. So it's the space of scalar fields on RD with values in U of n. We take the Moyal-Veil product that I introduced earlier, and now we just define a star commutator. Okay, so we deform the usual U of n Lie bracket by putting in star products. So U of n is, of course, a matrix Lie algebra, so you can write its bracket as a commutator, and now we just insert star products. Okay, and the fields here these are star products, but the fields are also multiplied with respect to the color indices of the group here. So this bracket satisfies the Jacobi identity. That's because the Moyal product is an associative product. So just on general grounds, if you take the commutator in any associative algebra, that defines a Lie bracket. Okay, so this space omega 0 RDU of n is an infinite dimensional Lie algebra. And I'm going to denote that Lie algebra as U star n. So it's not U of n, but it's the U of n valued functions on RD with this deformed Lie bracket. Okay. I'm going to talk about homotopy algebras soon, and you don't need to know a lot about homotopy algebras to understand this talk. But if you do know about homotopy algebras, I'll just say in passing here that because this is a Lie algebra here, this means in particular that non-commutative field theories are just organized by ordinary L infinity algebras, okay, as has been observed in previous works. Okay, so that's going to be what a language we'll use later on, and I'll explain that in a bit more detail. But this is a consequence of this one. Okay, so what is this mixing that I talked about? So this space here, as a vector space, can be split into a tensor product. So it's a tensor product of the U of n as a vector space with omega 0 RD. Now, if you were in the commutative situation, you would know that this Lie algebra of U of n valued fields on RD also factorizes into a product of the usual U of n Lie algebra with the commutative associative algebra of functions on RD. So that would hold at a kind of algebraic level. But this does not hold in the non-commutative case. So as a Lie algebra, there's no U star of n does not factorize like this unless theta is 0. And that's just from an elementary calculation. If you expand your fields here in a basis, let's call it TA, of the Lie algebra U of n, and you compute this star commutator, you find that there are two contributions. Okay, so there's one involving the structure constants of U of n, but then there's another combination that involves these symmetric structure constants coming from anti-commutators. Okay? So these symmetric structure constants come into this relation, of course, because when you go and if you go and expand and calculate, of course, this bracket in here is a star bracket between ordinary scalar valued fields. Okay, and if theta is non-zero, then this bracket here is non-zero. So if theta was 0, of course, you would be only left with the first term in the brackets here, and that would be just this, and this star anti-commutator would just be the usual product, and you would just have the statement of a factorization here, which would amount to giving color stripping in a standard theory with color. But here, there's some kind of a mixing. There's an extra term here that prevents this factorization. So this spoils color stripping. We can't just strip color from it. And hence the notion of color kinematics duality at first glance doesn't seem to make much sense in these non-commutative theories. So that's this problem. That was this question I meant, is what do we mean by color kinematics duality? Okay. So on the other hand, this lack of color stripping also provides will provide later on a novel realization of some of these kinematic Lie algebras that I was talking to. And that's one of the nice things about the non-commutative theories. What we'll end up with is some very precise answers for what their kinematic Lie algebras should be. Okay, so if we take this bracket now and we take a kind of a colored momentum space basis of plane waves, these EKAs, I'll define up here. Then we could, this is the basis, and we can calculate what the commutator is in that basis. And so there are some structure constants that I've written down like this. Okay, so again, in the commutative limit, theta goes to 0. This product, the sign will just be equal to 0. This cos will just be 1, and you'll get the usual Lie algebra factorization with no momentum dependence. Now what's interesting here is if you look at the rank 1 case, so the non-commutative U of 1 theory, then this just makes the space of ordinary fields, no color, into a kinematic Lie algebra. Okay, so what we're doing is we're putting these FABCs to 0 because it's going to be the U of 1 group. And these Ds, which come from taking the anti-commutators, right there, you just put them equal to 2 in this case. That's the anti-commutator. The generator of U star of 1, the Lie algebra is just it's just the number 1. So its anti-commutator is just 2. Okay, so then you get an algebra which looks like this, an infinite dimensional Lie algebra, where the structure constants are given by signs, sign factors involving these momenta here. So in the semi-classical limit, what happens is that this star commutator of just ordinary functions with no colors reduces to the Poisson bracket determined by this constant bivector theta. So remember, theta is a constant bivector, so it defines a constant Poisson structure on RD, and you have a Poisson bracket. And so in the semi-classical limit, this algebra just becomes a Poisson algebra. And that's, of course, we know what this algebra is in that limit. It's just the algebra of symplectic diffeomorphisms, the diffeomorphisms that preserve this Poisson bracket. So this kinematic Lie algebra, U star of 1, is a type of deformation of this Lie algebra of symplectic diffeomorphisms. And this was studied again many years ago and also more lately. It's related to various known Lie algebras, for instance, the infinite unitary Lie algebra, and also a special type of W algebra called W1 plus infinity. So this was studied again from the late 80s, and it's also been revived in some more recent work on the double copy. Okay. So there's some interesting kinematic Lie algebras that will pop up later, and they're also related to some algebras that we saw that have been observed in the double copy literature recently. Okay, so maybe I should just ask if there are any questions at this point, because I'm gonna. No, okay. So let's move along. Okay, so as I said, this talk I'm going to address this notion of a double copy in the language of homotopy algebras. And this is based on work due to these five people here from a few years ago now. And this is a beautiful perspective, in my opinion, on the double copy. It's very systematic. It's at the cost of perhaps being a bit mathematical, but it's a very, very precise way of taking the double copy in a language where you can just construct everything very explicitly. So the starting observation is that any theory, any field theory that has a BV formulation, so it can be formulated in the Batalin-Vilkovisky formalism, is equivalent to a theory with only cubic interactions. Okay, so this is just a statement. If you have any theory with arbitrary order interactions, then by including suitable auxiliary fields, you can always turn those interactions into cubic interactions, okay? From the point of view of the BV formalism, the BV formalism is dual to the formulation of field theories in terms of what are called L-infinity algebras. So these are homotopy algebras. If you don't know much about L-infinity algebras, don't worry, you actually don't need to know what they are, because I'm always going to apply what's called the strictification theorem for L-infinity algebras, which shows that essentially they're equivalent to what are called strict infinity algebras. And a strict L-infinity algebra just means a differential graded Lie algebras. Okay, so if you don't know what L-infinity algebra is, just think differential graded Lie algebra, which I'll mention on the next slide. But yeah, this is the general situation. Okay, so suppose L is the strict L-infinity algebra of your theory, and suppose that it has a factorization like this. Okay, so the theory is based on some color Lie algebra, and we assume it factorizes like this. So this kin, this factor here, is a finite dimensional kinematical vector space. So it's a vector space which is going to encode the kinematics of my theory. This scale that's written here is a strict L-infinity algebra of cubic scalar theory. So just the ordinary cubic, the scalar field theory with cubic interactions, no color. And this tensor product inside the brackets with the subscript tau is something called a twisted tensor product. And it defines something called a strict C-infinity algebra. Okay, and I'll mention a bit what this is technically on the next slide. But you suppose that you have a factorization of this. And this factorization that's written here is just, it's an algebraic incarnation of this color stripping that was used in the double copy. Then what's beautiful about this is that this homotopy double copy prescription tells you that if you have a factorization of this, then the double copy, the homotopy algebra, which governs the double copy theory, is obtained by replacing this color factor by another factor of these kinematic vector spaces. Okay, so it's given by some twisted tensor product like this. And the claim is this is how you double copy a gauge theory to a gravitational theory. Okay? And the homotopy zeroth copy, it says that you should now replace these kinematic factors with another copy of a possibly different gauge algebra, G bar, like this. So you get this L-infinity algebra here, and this is the L-infinity algebra of what's called this biadjoint scalar theory. So I denote this by BAS. Okay. So this is a beautiful perspective on the double copy. You see, if you understand all the words on the slide, you can write what the prescription is on one slide. Of course, the caveat here is that this mathematical decomposition here must be compatible with color kinematics duality in order for this final theory down here to make sense as a type of gravitational theory. So you need to check that by hand. So there's still some physics input into this, but it's a very, very beautiful and powerful technique of describing the double copy. So just one quick slide to maybe give a bit of mathematical background here. So as I said, a strict L-infinity algebra is just a differential graded Lie algebra. So it's a graded vector space together with some differential. Okay, so this differential has degree 1, and it squares to 0. And then it comes with an operation mu2, which is just a Lie bracket. So it satisfies it's antisymmetric, graded antisymmetric, and it satisfies a graded version of the Jacobi identity. And there's a compatibility condition between the differential mu1 and the bracket mu2, which is like saying that mu1's a derivation of this Lie bracket. So any such theory comes with the Maurer-Cartan theory. And the Maurer-Cartan equations on degree 1 elements give you the equations of motion, which I write in this form over here. Okay, so these are like what general are just the Maurer-Cartan equations of a differential graded Lie algebra. But these are what give the equations of motion of your physical theory. And likewise, if we have a cyclically invariant inner product on this differential graded Lie algebra, we can construct an action functional called the Maurer-Cartan functional using that cyclic inner product. And the variation of this functional with respect to these degree 1 elements V just gives these equations. Okay? So this is the key message to understand here, is that given the algebraic data of a differential graded Lie algebra, there's a Maurer-Cartan theory associated to it, which is your physical theory. It gives you the action functional, or just the equations of motion. So I mentioned this notion of strict C-infinity algebra before. So again, just think differential graded commutative algebra. Okay, so again, it's a graded vector space C with a differential. And now a graded commutative product, a multiplication on that algebra, such that M1 is a derivation of that product. Okay, so that's what we mean by a strict C-infinity algebra. Okay, so the twisted tensor product I introduced this is a lot to absorb in just a few minutes on a slide. So I just want to show you that this is all sort of well prescribed because we're going to use it a lot in the rest of the talk. So if I take a finite dimensional graded vector space and some differential graded algebra, okay, not necessarily commutative, then a twist or a twist datum is a pair of maps, tau 1, tau 2, that look like this. Okay, so you take this vector space V into the tensor product with the endomorphisms on the algebra A, the linear endomorphisms of the algebra A, and here tau 2 takes the tensor product of V with itself to this tensor product here. Then we can define a new differential graded algebra called the twisted tensor product. The underlying vector space of that DG algebra is just the ordinary tensor product of graded vector spaces of V and A. And then you just deform the differential and the multiplication maps of your original DG algebra. Okay, so I'm going to write it in Sweedler notation. The twisted differential on a tensor product of two elements. So the Sweedler notation means that the target map, the one superscript and the two superscripts land in the respective legs of the tensor product over here. Okay, so you take the twist map tau 1. The first leg lands in V, and then you tensor that with the differential of the ordinary algebra, where the second leg, that's now an operator on A, is acting on the corresponding second leg here. Okay, so it just takes a few minutes to stare at that and understand precisely what it means, and we'll use this in examples later. And then likewise, there's a formula for twisting the second the multiplication in the algebra. So again, we use the Sweedler notation for the legs in this triple tensor product, where the second legs always land in operators on A. So we just let them act on the corresponding factors here in this fashion. So there are some sign factors, some annoying sign factors you have to keep track of here that come from the fact that it's graded. So I'm not writing them explicitly, and I'm just denoting them symbolically with plus or minus. Okay, so what the twisted tensor product is, it's an operation that moves you between L infinity algebras, so in particular differential graded Lie algebras, and C infinity algebras, or differential graded commutative algebras. Okay, so in other words, if I have a differential graded commutative algebra and I take a twisted tensor product of it with a vector space, I get back a differential graded Lie algebra. And conversely, in the other direction. Okay, so let me move along. This is kind of the technical tools that we're going to use to discuss finish off the story here. So let's look at this in the language of the kind of what I call the commutative skeletons. These are going to be the building blocks of all the theories that we look at today. So the first is the scalar field theory. So what is the differential graded Lie algebra of scalar field theory? Well, there's a differential on a graded vector space. So in the case of this theory, the cochain complex looks like this. It has two components, two graded components in degree 1 and degree 2, which are just copies of the functions or scalar fields on RD. It's got a non-trivial bracket and a pairing, which looks like this. So the bracket is just the ordinary pointwise product of fields. Okay, so when the fields here always live in this degree 1 component. And the only non-zero pairing is between a field in degree 1 and degree 2. So I distinguish those by saying the fields in degree 2 have a plus superscript, and I just take their product and I integrate them. Okay, so you go back to what I said about the Maurer-Cartan theory. You put this data into the formula for the Maurer-Cartan functional, and you just see that it reproduces the action for massless scalar phi cubed theory, okay, with this coupling constant inserted into the product. Okay, probably the simplest homotopy Lie algebra you can write down for physical theory. Okay, the other theory now is the bi-adjoint scalar theory, where I'm going to kind of dress this theory with color, actually dress it by two sets of color factors. So it's not a gauge theory. It's a theory that has a rigid symmetry under a pair of Lie algebras, and in particular, they're quadratic Lie algebras. So they each come with an invariant inner product, an ad invariant inner product. And then this corresponding homotopy algebra or differential graded Lie algebra. Again, there's a cochain complex from the fact that we've got a differential. The differential is still this wave operator box. Okay, and now I modify the product slightly here to include the color and as well the inner product by these formulas here. Okay, so this product here now is something that looks like a double Lie bracket with respect to these Lie algebras, and in fact, it's just the tensor product of the two Lie brackets, and then the inner product is just obtained by contracting the components of fields and then integrating them. Okay, so it's just an extension of what we wrote up here. And now, again, you turn the crank, you go to Maurer-Cartan theory. I've got all this algebraic data, and you can write down what the action functional is. And this is the action functional that defines this theory called the bi-adjoint scalar theory. Okay. And the thing here to note, and I had this on a few slides ago, is that this L infinity algebra factorizes into a product. Okay, so if we start from this L infinity algebra scal up here for the ordinary cubic scalar field theory, then this L infinity algebra is just the tensor product with these two Lie algebras and this L infinity algebra up here. Nothing twisted, just the ordinary tensor product. Okay, so this is this algebraic relation I wrote down a few slides ago. And you could just go through carefully. It's looking at all the formulas up here on the structure maps and convince yourself that that's in fact true. Okay, so now we'll deform this. I'm going to look at a theory now that'll come back towards the end of the talk mostly. But this is just I want to illustrate now how we're going to solve this kind of issue with color kinematics duality. Okay, so I'm going to define something I call the non-commutative biadjoint scalar theory. And by the end of this talk, you're going to be fed up with hearing about these biadjoint scalar theories. There's going to be lots of them coming in. But there are some interesting ones coming up. So what we'll do is we'll take the ordinary biadjoint scalar theory and we'll replace one of the Lie algebra factors by a copy of this infinite dimensional Lie algebra U star of n that we defined before. Remember, this was the thing that mixed color with kinematics. And by doing that, we can use, remember I wrote down the formulas for the star commutator, and using that, we can get again, a strict L infinity algebra, Bas star. It has the same underlying cochain complex, but now you just deform the bracket or the binary operation to this quantity here. Okay, so you can see what's inside the brackets here should look familiar as what I wrote down earlier when I was talking about the star commutator. So you have this L infinity algebra here now, an ordinary L infinity algebra. You apply the Crank-Maurer-Cartan theory, tells you how to write down from this data a action functional. And the action functional looks like this. It looks very much like the biadjoint theory, except for the second set of structure constants, I also have to introduce these d bars, which come from anti-commutators of the generators. And of course, I've got star products in the interactions now. Okay, and if you wish, we can try to visualize that by looking at this interaction vertex in momentum space. In momentum space, the interaction vertex looks like this, where these F, K, P, Q are the structure constants I wrote down, the momentum-dependent structure constants I wrote down before for this infinite dimensional Lie algebra U star of n. And they simply come from replacing the usual structure constants in the usual biadjoint scalar vertex by these momentum-dependent factors. Okay, so that's another way to think about how this deformation is working. Now, the crucial thing is here that these factors, these F bars of KPQs, they cannot be split into products of the structure constants and just kinematic factors, right? And that's, again, what I said before because of the mixing up here, okay? So that's the whole point, that this, unlike its commutative version, the non-commutative biadjoint theory cannot be factorized. You can, of course, factorize one Lie algebra, but the U star of n cannot be factorized in this sense. Okay, and of course, it doesn't really make sense because this U star n already has mixed into it some kinematic factors. It's not just a color Lie algebra. Now, what is true is we can factor out, of course, the left Lie algebra, the one that involves these structure constants without bars on them. Okay, so you can factorize that into a tensor product of the Lie algebra G with a differential graded commutative algebra or strict C infinity algebra, which as a vector space is just the vector space of functions an RD, but valued in U of n. So they're matrix valued functions. And again, it's a differential graded commutative algebra. So there's a cochain complex controlled again by this wave operator. The product here is now just the star commutator of ordinary fields. So this is the star commutator I wrote down before. And now the cyclic inner product is just you take the trace of a product of fields and then you integrate it. Okay, so here's this strict C infinity algebra. And this is the problem. This cannot be factorized using tensor products, but it can be using twisted tensor products. So this we factorize now as the tensor product of the ordinary U of n Lie algebra. So that gives us this finite dimensional vector space U of n with the scalar cubic scalar theory. With a twist datum, that's defined by these formulas. Okay, so it's essentially just acts as the identity operator at the level of differentials. But on the what's going to twist the product is given by this formula here. And you can sort of see what this operator is doing. This operator is what's coming in and putting in the star product factors. Just go back here, that appear inside here. That's what these sines and coses are doing. They're just the same sines and coses I had before in momentum space, but now they're written in position space. Okay, so it's a bit of writing out the form I presented here, but this is the claim that we can factorize this as a twisted tensor product into this form over here. Okay, so the key thing is that inside the brackets here, I've got a twisted tensor product, and you can really check that this statement holds through. Okay, so here, this is stripped now color from kinematics at the expense of it talking about twisted tensor products. And everything, all the factors in the tensor products here are just commutative objects, right? The non-commutativity is completely absorbed into this twist datum here. And this is, from a technical perspective, what resolves the problem, the sort of what I talked about earlier about what is the meaning first of color kinematics duality in these non-commutative theories. Okay, so that's just illustrating how this works. Now let's start applying this to some concrete situations. So let's talk about a simple double copy theory. So we'll start with Chern-Simons theory. Look at the well-known non-commutative deformation of Chern-Simons theory. So it's given by this action functional here. So we just do the usual deformation, take Chern-Simons, we deform it like this. And this is organized by a very simple L-infinity algebra. Okay, there are only cubic interactions here, so it's still a differential graded Lie algebra. Okay, so the bracket here is just the usual commutator bracket, but understood in terms of differential forms. The differential is just the usual de Rham differential. And your graded vector space is just the usual exterior algebra of U of n valued forms on R3. Okay, and the pairing, the cyclic inner product, is just given by taking the wedge product of forms, tracing out the color part, and then integrating. So if you wish, the three gluon vertex in momentum space, the interaction looks like this. So there are these, of course, kinematic type structure constants, these epsilons here. And instead of a purely color factor, you now have these momentum dependent structure constants. And so what this theory shows at this level is there's a twisted form of color kinematics duality. In the interest of time, I'm not going to explain a lot what this says, but there is a twisted form of color kinematics duality that you can just naively read off from this vertex here that says that the the numerators factorize into twisted tensor products of the Lie algebra U of n with the infinite dimensional Lie algebra of volume-preserving diffeomorphisms of R3. That's what these epsilons are, very roughly speaking. Okay, so I don't want to explain this too much because I want to really get to the punchline here. Okay, so we can talk about a twisted form of color stripping, again, of non-commutative Chern-Simons. So we can again factorize Chern-Simons as a twisted tensor product with a C infinity algebra that looks like this. So this is now just this C omega bullet is just the ordinary exterior algebra of differential forms in R3, right? Where the differential is just the usual de Rham differential. The product is basically just the exterior product, and then multiplied with this coupling constant G. Now this is just a commutative object, but this can be factorized as another type of tensor product, and this has nothing to do with non-commutativity. This type of twisted tensor product is coming because of the non-trivial kinematic factors that are present in just ordinary Chern-Simons theory. So I can factorize it with a twisted tensor product between the L infinity algebra of my cubic scalar field theory, SCAL, and a kinematical vector space that I call kin. That's essentially just the exterior algebra of the dual of R3. Okay, so there's some technical details about degree shifts and so on here. And the twist datum is just defined by these formulas here. Okay, where these E's here are given by a basis of covectors in R3. So the claim is that this differential graded commutative algebra factorizes into this twisted tensor product. Okay, and it's again just a matter of turning the crank of the formulas I wrote down before for the prescription of doing twisted tensor products. This 1 over box appears here, of course, because the differential of SCAL is the wave operator. So you need to cancel it in some way to get the differential of the de Rham complex up here. But anyway, you go and you check that. And so you see that altogether, you have a twisted factorization of non-commutative Chern-Simons theory into this form. Okay, and this turns out to be compatible with this twisted form of color kinematics duality that I wrote down before. Okay, right, so now we can double copy this. So with the way we double copy in this twisted language is instead of whenever we have a twisted tensor product, we just strip away color, but with that twisted tensor product. Okay, so you see we get a double copy algebra that looks like this. And the point is here, there's no non-commutativity anymore. This is the same double copy you would have gotten if you just started with ordinary commutative Chern-Simons theory. Although this was the first time that it was written down in this homotopy double copy language. And you can show that it gives the double copy theory agrees exactly with the known double copy theory that was written down by these people based on more kind of physics-oriented approaches to the double copy. Okay? And again, the Maurer-Cartan theory, you can work out what that is. It's the physical fields are some type of spin 2 fields that you can roughly think of as products of gauge fields from the left and right sectors. And they come with this highly non-local action functional given by this formula here. Okay. And this comes about, of course, because now once you've stripped away, you're taking two twisted tensor products here, and only one of the box operators will get canceled in that prescription. Okay, so it's not this theory isn't gravity, of course, but it's some theory that has a type of diffeomorphism invariance. It's been rederived before in the context of double copy from many different perspectives, but this is a derivation of it in the language of homotopy algebras, and in particular, in this case, in the language of non-commutative gauge theories. So the upshot here, and I'm just about out of time, but if I could have a few more minutes, I want to go and answer the question 1, which I haven't answered yet. But anyway, the upshot here is this explains why double copies of non-commutative gauge theories are just the ordinary double copy theories. Okay, so this was the boring result I had before, but you see we had to look at this from a theoretical perspective quite deeply to understand why this homotopy algebraic formulation gives us that result. Okay, so let me just quickly finish off with a few more slides. So if you allow me a few more minutes, I will just come and answer the first question I had. So there's a very interesting theory. We have this non-commutative biadjoint theory, and this theory has a very interesting rank 1 limit. So let's put n equal to 1 in this non-commutative biadjoint theory that I wrote down before. Okay, and what you get then is you get a differential graded Lie algebra that looks like this, where the product is now given by this formula. So remember, there's only one Lie algebra now because we've gone to the rank 1 limit of the U of n part. Okay, and the pairings like this. And note, this is not the star commutator in this Lie algebra G. Okay. In particular, if you turn off the non-commutativity, this product vanishes. And what that means is this is an example of a non-commutative field theory that's trivial in the commutative limit. There is no commutative analog of this theory, no interacting commutative analog of this theory. It's really a non-commutative phenomenon, let's say. Okay, so you can work out the Maurer-Cartan theory of this, Maurer-Cartan theory of this, and you find this action functional. And again, you can easily check that the interactions go away in the commutative limit when you erase stars. The 3-point Feynman vertex is what you expect. It's the product of the Lie algebra G with the kinematic Lie algebra U star of 1 that I wrote down before, and now really just the ordinary tensor product. Okay, and so this theory has a kinematical algebra, which we can identify as this Lie algebra U star of 1. Okay, and so we can double copy this theory. Okay, there's a compatible twisted factorization again, which I won't spend a lot of time on, but we just follow the same logic we had before. The 0th copy of this theory here is just going to give the commutative biadjoint theory, where we replace this kinematic factors, which is just this one-dimensional vector space R now, with another Lie algebra factor. And then I just turn the crank, I apply this homotopy double copy prescription, and I get a complicated product, double copied theory with a complicated product that looks like this. And this is what the Maurer-Cartan action functional looks like. It's quite a complicated theory, but it is what it is. It's again some new theory, and that's what it looks like. Okay, so yeah, apologies for going fast here, but I want to get to the answer. So just quickly a couple of slides. So we can now, this double copy theory that we have here, we can generalize and just put color in. So we'll just define a theory whose L-infinity algebra has 2 copies of color given by these twisted tensor product. And I'm not going to write out the details. The details are a bit lengthy. But there's a product, so by the way, I call this the bi-non-commutative biadjoint scalar theory. So as I said, there's a lot of scalar theories coming up here. So this is just if you take the product that I wrote down over here, and then you just turn it into a non-abelian thing in each factor. Okay. The Maurer-Cartan theory is very long to write down, and I won't write it, but in momentum space, it has a very simple representation if we look at what the vertices are. Okay. Okay, so they're given by these structure constants, momentum dependent structure constants from before. And now the tree level amplitudes in this theory can be color stripped, and then you can show that they can be obtained from the commutative biadjoint theory by just dressing them by phase factors. Okay, so the tree level amplitudes in this theory are just given by dressing the commutative color stripped biadjoint scalar amplitudes in this theory. Okay, so this non-commutative biadjoint scalar theory is the non-commutative version of the zeroth copy theory. Okay, so in particular, you can easily see in the case of Chern-Simons that the zeroth copy theory in the space of these non-commutative theories is just this non-commutative biadjoint theory, which again I stress is some new theory, and it's a highly non-trivial theory, even though it acts like the identity. Okay, so my last slide, and this is just saying what happens with non-commutative Yang-Mills theory. Again, I can write down the action functional for non-commutative Yang-Mills theory. There's a bit of a story here about the double copy because, of course, the interactions here are no longer cubic. So they're quartic interactions, which means there's a non-trivial product, and the underlying L-infinity algebra is not a strict L-infinity algebra. But you can strictify it, that is, turn all your quartic interactions into cubic interactions by introducing suitable auxiliary fields, and the twisted color stripping are possible, but they have to be compatible with color kinematics duality at each order. Okay, so I'm not going to go through any of the detail, but the upshot is we go back now to a slide 2 or something two or three, when I had the KLT momentum kernel, and that appears in the KLT double copy relations with a B field, and remember, those now will involve in the field theory limits the amplitudes of this theory here, of non-commutative Yang-Mills theory. And what you can show now, what is the thing that dresses them? Well, if I look back to what I said here about this non-commutative biadjoint scalar theory and its relation to the ordinary biadjoint scalar, we see that the KLT momentum kernel is now sourced by the non-commutative biadjoint scalar theory. And that answers question 1, which I posed way at the beginning of the talk, is what is the scalar theory that's involved in this kind of B field modified KLT double copy? And as you see, it's actually a very non-trivial scalar theory. Okay, so I'm going to stop there, and I apologize for going over time, right? Thank you.
Okay, thank you very much for very interesting talk. Uh, okay, so now it's open for discussion. And is there any questions or comments?
Can I have a question?
Yeah.
Yeah.
So is it possible to realize this homotopy algebra theory to